In this video, I want to clarify a few concepts or other misconceptions that exist in engineering dynamics as well as in physics. And one of the misconceptions relates to the direction of the friction forces. So it is commonly thought that friction forces always oppose motion. And to give you a simple example, let's say we have a particle over here on which you apply a force F in the right hand side. Then there is relative motion between the particle and the ground. And that means that the friction force would oppose this motion, and that means that the friction force would act in a direction opposite to this force F applied. And that means if you draw a free body diagram, it would look like this. F sub F is the friction force, that's the normal reaction, and then you have the gravity. Okay, so in this case, since the particle is sliding towards right, the friction force is opposing that relative motion, and that's why friction force is pointing towards left. If you take a wheel and the wheel is slipping, which means that it is actually moving towards right hand side like that, and there's a force applied to make it move that way, and it is sliding. So it is just like the particle. So if I draw this line over here, the particle or the wheel over here is in this position, and this line is still vertical. This line is still vertical. Okay, that's the friction, that's the force. Then the friction force on this is pointing in the opposite direction, because if you look at this point over here, the bottommost point on the wheel, that point has a relative velocity with respect to the ground. So the relative motion is towards the right, and that means friction force is opposing that motion. Okay, and this is true. This is something that everybody understands very well, right? But now let me ask you a different question. I have a car. It doesn't have to be a car, it will be a bicycle, motorbike, doesn't matter. And this car is actually accelerating towards the right hand side. Okay, so it's accelerating with some acceleration. The question is, what is the direction of the friction force on the wheels, both rear as well as front wheels? So first of all, I have to tell you what kind of car it is. Is it a rear wheel drive car? Is it a front wheel drive car? Is it an all wheel drive car, right? So there are three scenarios: rear wheel drive car, all wheel drive car, front wheel drive car. So let's take the example of a rear wheel drive car. So this car is driven by an engine or a motor that is powering the rear wheels only, and the front wheels are passive. They are allowed to roll, but there is nothing powering them directly. And the car is accelerating with some acceleration to the right hand side. Okay, so what is going to make this car actually move towards the right hand side? Where will that force to make it move towards the right hand side come from? It's going to come from the interaction between the wheels and the ground, right? Because the engine is directly powering the wheels are in contact with the ground. So the wheels have to provide that, the ground has to provide the force to make the car move forward. So if you draw the free body diagram of the car, you have the normal reaction. Let's call this point A, this point B. Okay, and here is the center of mass. So you have reaction NA, we have reaction NB, we have the weight of the car acting downward, okay? And then we have the friction forces, which will make the car move to the right. So friction force on the rear wheel act in the forward direction, because it's these friction forces that actually give rise to the motion of the car or acceleration of the car towards the right hand side. But the front wheels are not powered, so the friction force on them point in the opposite direction, okay? So the direction of the friction forces are different, even though the motion of the wheels are clockwise for both front and rear wheel, but you can clearly see that the direction of the friction forces are different, and they are dependent on which wheel has the torque applied on it, right? So from the engine, there is a torque applied on the rear wheels that's making the car go forward. The front wheels are simply transported forward because the rear wheels are pushing them through the frame of the car, right? And those are the directions of the friction forces. So if you were to do the analysis using Newton's second law on this car, then you would simply say sigma F equal to mass times acceleration of center of mass, and the forward direction forces are Fa, and the backward is minus Fb. So clearly Fb is opposing that motion, and that would be equal to m times A0. And this is just writing in the x direction. Clearly in the vertical direction, things are trivial because the normal reactions have to balance out the weight of the car, right? So as long as Fa is more than Fb, you will have some non-zero acceleration. If Fb became more than Fa, then of course you won't have an acceleration in the forward direction. Now let's see what happens if we remove the friction between the ground and the car. So if there is no friction between the ground and the car, then you know intuitively that the car is really not going to move forward, right? So what is going to happen to the rear wheel and the front wheel? Well, you know the rear wheels, even though you're applying a moment on them, are going to slip because there is no friction between the rear wheel and the ground. So that means that the rear wheels are actually going to slip. So if this is the initial position of a line, then after a while, you know, it would be this, it would be this, it would be this, but it's basically just rotating while its velocity in this direction is 0, okay? What is happening with the front wheels? Front wheels are unpowered. So the front wheels are actually not going to even move. There is no friction. There's no friction acting on the front wheel. So if you draw a free body diagram by itself, there is no friction. There is the normal reaction. This is NB, and there is the weight of the wheel, okay? So let's say that's simply W, and there is no other force on it. That's it. So N is balanced by the weight. There's no friction force to even make it rotate in this direction or that direction. So if you have a line in this wheel, it always remains vertical. So this one is slipping and this one is stationary. So this is the no friction case, no friction case. Okay, and this one is the friction case. So you do have the friction. All right. Now, how would the things change if, let's say, you have an all-wheel drive car? If you have an all-wheel drive car, so both of these things are done for rear-wheel drive car. If you have an all-wheel drive car, what will change is that you will have both the wheels, front wheels and rear wheels, powered, right? And that means that the friction force on both the wheels would be in the forward direction. So let me draw that. For all-wheel drive car with friction, the force of friction at A and at B would be pointing in the forward direction. For front wheel drive cars, because only the front wheels would be powered, so let me write that, front wheel drive car with friction, this is point B, this is point A. The force of friction would be in the forward direction because the front wheels are powered, okay? And on the rear wheels, the friction would be now pointing in the opposite direction, just as was the case with the rear wheel drive car, where the friction force on the front wheels, which were the passive wheels, which were just allowed to rotate, was pointing in the opposite direction. The same case with the rear wheels for a front wheel drive car, okay? So basically this tells you how the friction forces act, in what direction they act. So you have to know whether the car is accelerating or decelerating and what kind of drive it is, and based on that you can tell which direction the friction forces are acting. So this is the misconception, right? Because you can clearly see that friction forces are not always opposing the motion, and when you say that, you always have to ask the question, motion of what? Is it the car? Is it the wheels? And so on, okay? Misconception number 2 is that friction forces always reduce the energy in a system. In general, that is not true actually. So if you look at just this case where we had rolling without slipping, okay, so let's say we're talking about rear wheel drive car, and I'm going to draw that free body diagram again, but this time I'll just draw the rear wheels. So rear wheel drive car, and this is the rear wheel. Let's say this is point B. What did we choose? This was point A. This is point A. So we had friction force Fa acting that way. You have the torque M0 from the engine. You have the gravity, and you also have some vertical and horizontal direction forces transferred to the wheel through the axle, right? And this could be the weight of the car that is being applied at the center of the wheel, the vertical direction and the horizontal direction force as well. So these are the forces acting on the wheel and the normal reaction, right? So clearly NA is not going to do any work. We know that because the wheel is moving in the direction which is perpendicular direction of the normal reaction. V and H, V will not do any work, Mg will not do any work. Clearly H will do some work, What about F sub A, the friction force? Is FA doing any work? So this may come as a surprise to you, but in this particular case, the friction force is actually not doing any work in making the wheel go in the forward direction, because under the rolling without slip condition, the point A actually has zero velocity. This point is actually not moving. Okay, so that means that there's no work done by FA. And if, let's say, math is what you like to see exactly whether the work done by the friction force A at A would be zero or not, you can see that. So dW is F dot dr, right? So this is FA times FA dot dr over dt times dt. So this is actually point A, so we'll just write that. So this is FA dot VA dt, right? That's dW, and W is integral dW, which is integral FA dot VA dt. But VA is the velocity of the point A, which is zero. So that means that the work done by the friction force at point A is zero. So the friction forces actually will not do any work. This friction force will not do any work. The friction force over here will not do any work either, the FB, which is acting in the opposite direction, but it is also not going to do any work because the point B is at zero velocity. So this may, give rise to the question, well, are there any losses then in that case? Well, in reality, there are losses because, wheels have the tires on them, and the tires are made of a material called viscoelastic material, which have hysteresis property, which says essentially that their deformations are not elastic. So for elastic deformations, as we had seen for elastic impacts, the energy is conserved in the process of impact. Or in elastic deformation, the energy required to take the deformation, to do the deformation, is actually equal to the energy when the matter regains its shape. So in case of a viscoelastic material, which is what is used to make the tires, there are hysteresis losses, okay, and there is also deformation of the tire. So all of that is characterized by something called rolling resistance. So there's something called rolling resistance, which should not be confused with friction forces. So rolling resistance is entirely different from friction forces. So if you look at, let's say, a wheel with tires on it, and let's say the wheel is stationary, then in reality, the wheel would deform to some extent, okay? Or the ground could deform to some extent, okay? So this is going to be a patch over here, but this patch would be such that the normal reaction due to the pressure distribution in this patch is going to be acting in a direction vertically up that will oppose the weight of the wheel. On the other hand, when this wheel begins to move, the geometry of this patch actually changes. The geometry of this patch changes, and the pressure distribution may look something like this. And the resultant normal reaction, because of this geometry of the patch, may be that the normal reaction is acting this way. Okay, so it's not exactly vertical, which will oppose just the weight of the wheel, but it is actually at an angle. So if it is an angle, then it can have two components. One is the vertical, which will oppose the gravity, and another one that could be in opposite to the direction of the motion. And this is clearly acting in direction opposite to the motion of the car, right? So notice how this rolling resistance, let's call it R sub R, is different from the friction force acting on the rear wheel, right? And this rolling resistance is mu R, another coefficient, just like you have mu S and mu K, but you've probably never seen mu R. Mu R is generally much, much smaller than mu S, times the same normal reaction that you have over here. Okay, so rolling resistance should not be confused with the friction forces. Rolling resistance can give rise to the losses because this rolling resistance arises from the deformation as well as the hysteresis losses. So here is a simple question for you to answer. So let's say we have a rear wheel drive car, which means that the rear wheels are being now powered. There is a torque applied on them. And this is point A, this is point B, right? And let's say there is friction between the rear wheel and the ground, and there's no friction between the front wheels and the ground. Maybe you're driving this car and you get stuck in mud, your front wheels are in the mud, and there's not that much friction available to you, but your rear wheels still have the friction. So now, if you power the car, if you apply the torque on the rear wheels, how would the car move? Is it going to move, first of all? Well, if you draw the free body diagram of the car without the ground, then you will have friction force Fa pointing in the forward direction. And that means that the car is going to move forward, right? because there is some friction force available to you. There's no friction on the front wheel, which means that there's nothing to make the wheels rotate, right? The front wheels rotate. So the car is going to move in that case, but the way it will move is the front wheels will not change their orientation. So if you have this line, after a while, this line would be maintained, which means that the front wheels would be essentially just translating while the rear wheels would be rolling without slipping.